Today's lesson is on vectors. And just to start off, this is just an introduction to vectors. You will go over vectors in great detail when you get to pre-calculus and beyond, hopefully, in the field of engineering or mathematics or physics, and there's all kinds of things that vectors can be used for. But today we're going to have an introduction. And the definition of a vector is a quantity that has magnitude with direction. And I have one example of a vector, or not describing a vector, a wind from due north at 30 miles per hour. The vector this is your quantity, and this is my magnitude is 30 miles per hour. And this is my direction, of course, right here. And we draw vectors to help us solve problems. So if I was going to draw this, I would draw a scaled vector. So I would mark my north. I would draw 30 miles per hour. And how am I going to draw 30 miles per hour? Excuse me. Well, what I'm going to do is just pretend it's 1 hour. In 1 hour, it would go 30 miles. So 30 miles, I'll go 3 centimeters. And notice that I put an arrow showing me which way it's going. So it's from due north, and I'll put a 30 miles per hour and mark it. And that is my vector. Two essential parts of a vector is every vector has a tail and a head. And the head, you can tell, is where the arrow is. This vector, I could also, if I wanted to redraw it, I could name it different ways. Oops, I went too far. I could call it vector W. And notice that it has like an arrow over there, but it's only got one side. So there's vector W, and it's going, we'll see, there's my tail and my head going in that direction. Okay? Well, the direction of a vector can be described in terms of compass directions, like we did in this example, from due north. So we can, compass, of course, north, south, east, and west, yes? Thank your second grade teacher for never eating soggy waffles, I think. So we have compass directions, we have due north and due south, and we can also be in between there. So how am I going to say, well, I want a vector going that way? Well, there's a couple ways of describing that. Let's just say that is 40 degrees right here, which makes it 50 degrees on this side. There's a couple of ways we can describe that. We can describe that as north 50 degrees east. And I would write that north 50 degrees east, which means look at north and then go 50 degrees towards the east. I could also describe the same vector direction as east 40 degrees north. So that kind of makes sense, right? If you go east and then go towards the north 40 degrees. Notice that it's not going down in the south because my arrowhead's going that. That seems pretty straightforward. But that can be confusing. Notice I use this word bearing, and some of you have done some orienteering, might know the word bearing because of compass rose and such like that. So that is what I usually use. I use the compass rose and compass directions for the word bearing and such. Mathematicians, though, we like to describe the direction in one angle. And so the direction can be also be given as a single counterclockwise angle of rotation from east. So I still would have my north, south, east, and west. But now it's implied that we're always going to start here. And the one I gave earlier, 40 degrees this way, would simply be 40 degrees. Because east is going to be 0. And you don't have to say east 40 degrees north. That's what, if you give me a single degree measure, you're going to tell me I'm starting off at east and I'm going in a counterclockwise direction, this way, yes. And you'll tell me how far. So if I give you a single 300 degrees, well, that would be all the way down around here, over here, yes? Something like that. That would be a direction of 300 degrees. And we would not say east 30 degrees south. That would be the bearing. But a bearing of 300 degrees would look like that. All right. Another very useful instrument when describing vectors is a component form of a vector. And the component form of a vector lists the horizontal and vertical change from the initial point to the terminal point. And I have described the initial point earlier as the tail, and this would be the head. Yes. So if we're looking at our earlier example of a wind that had, what was it, a 30-mile-an-hour wind from due north. It was going this way. It was 30 miles per hour, and this was my north. If we list the horizontal and vertical change, well, in this case, I have no horizontal change. So I'm going to say 0. And the vertical change is 30. As a matter of fact, it's 30 down. And just like what you did before, as when we're doing coordinate geometry, that would be a negative 30 going down. So, and we're gonna put these in these funny brackets, such as that. They look like less than, greater than, but larger, right? So a component form 2,5 would mean I'm going over 2, positive direction, and up 5 in a positive direction. That's the X and the Y. You can always write, because there's my horizontal change. There's my vertical change. This is the vector that has those components. And let's call this vector U. And I can write that as, in component form, as 2,5. Great. And if I wanted to change the direction, let's make it negative, right? -5, -8. Just like before, you go backwards 5, and you would go down 8. The vector would go from here to here. And maybe that's vector W. Oh, I might as well say it. I could also say the points. It says initial point to terminal point. If these were points A and B, I could also make that equal to vector AB. And just like a ray, but half an arrow. Okay, so there's multiple ways to describe vectors, and there's also multiple ways to describe the direction. The magnitude is the other component of a vector, kind of like not component form. So we have a direction and we have a magnitude. And the magnitude is how long this scaled vector is. And we write it in symbolically as two vertical lines, very similar to absolute value. And the magnitude, let's say AB is the vector, and I'll tell you that AB, well, let's just use the one we had. AB had a -5, -8, right? And that looked like 5 this way and 8 this way. And if I want to know the magnitude, of course it is not scale drawing, I probably would be better. It's nothing more than how long is that purple vector? There's AB. And the magnitude would be the length. And if this is X and Y, this is a right triangle. So the magnitude of AB would be equal to, well, it's 8 squared, or -8 squared, it's still going to be positive, right? Plus 5 squared. And that magnitude, and of course, I've got to take the square root of that. Kind of look familiar, yes? 64, 25, square root 89. Simplify that. There's the magnitude of AB. Simple, simple, yes? All right. Let's look at some examples of how vectors will help us out. Okay, now this gets interesting. A plane flying north at 500 miles per hour with a headwind of 35 miles per hour. How far will it go travel, in 1 hour? Not too difficult to understand, but let's just draw the vector itself. Let's make a scale. Maybe I'm not going to draw a scale because that's 530 and 35. So if it's going north, flying north, there's my plane vector. And if it has a headwind, that's describing it's hitting it in front. The headwind is going to be going the opposite direction, right? And that's my wind vector. And as you can see, you're not going to be going 500 miles, right? Because when you put the two vectors together, one would going north and one's coming against us, I'm not going to go not that far, right? I'm going to go a little less. If I write the wind, like the plane, in component form, it even becomes more obvious. Component form of the plane, let's see, would be 0 horizontal change, 500 vertical change. The component form of the wind would be 0 horizontal change and -35 vertical change. The answer, otherwise known as the resultant vector, which is the answer, we'll just say, would be what I get when I put these two together. And what do I get when I put them together? I get 0, and you subtract them, 465 miles. So how far will it travel? 465 miles. All right. If the same plane was traveling but it's traveling south now, so the wind now, the plane is traveling this way, and the wind is going this way. Well, the wind's going to help me. And if I just change that out, that's not a 0. The wind now is still 0, -35, and the plane's at 0, -500. Well, the resultant in this case, of course, would be 535. So the plane using the same amount of energy actually goes farther. All right. Then it gets a little interesting, right? A plane flying north 30 degrees west, we can't leave it, just the way it was, at 500 miles per hour with a wind from due east at 35 miles per hour. The first thing I would suggest doing is draw a diagram. Okay, so north 30 degrees west. North 30 degrees west. It's going to go there at 500 miles per hour. So I didn't draw like I said. So this is my 30 degrees. This is 500. That'd be 500 miles because that's how it traveled in 1 hour. We can just if we were going to go 2 hours, it would be twice as long. It'd be 1,000. No problem. The wind from due east, so here's the east. From due east means it's going this way. So what's going to happen is the wind, and it's just a little one. I'll make it a little large. It's going to push me that way. And that's 35 right there. Okay? Where the plane ends up, the resultant vector is the combination of those two vectors. And this actually would be the path of the plane, this green line here. There's my resultant vector. We'll call it R. Right there. And strangely enough, if it was truly going 500 miles per hour and the wind was constant at 35, well, this is where the plane would be at different points. And in 1 hour, that's where it would be. Well, fantastic. But the question is, well, where is the plane and how fast did it actually, or how far did it actually travel? Component form helps us tremendously. The component form of the plane is, we can break it down. I'll use blue. It went 500 over there. It's 30 degrees there. It is 60 degrees on this part, right? If this is 500, 60, 90, oh, this is a 30, 60, 90. How nice is that? The hypotenuse is 500. The short leg must be 250. The longer leg must be 250 root 3. So the component form of the plane, so we'll call it vector P, component form, would be, and let's go, so we're going left and we're going up. So left 250, we'll say that's negative 250. Up would be 250 root 3. Exact answers. I like that. The component form of the wind is actually easier. That's going to be a 35 going this way. So we'll say that's negative 35. And a vertical change of 0. So the resultant vector has a component form of those two added together, which would be negative 285, excuse me, 250 root 3. Now, can you see how useful that will be? Because now I have made a right triangle for the green resultant vector, and these are the two side lengths. 285 is one of the side lengths, and 250 root 3 is the other side length. Now it just becomes, if you wanted to know how long that green vector is? A squared plus b squared equals c squared. Okay? That is how you do it. All right. So we'll do more problems like that next time I see you in class. And here are a little bit of problems that I hope are not too difficult. All right. What is the direction of 3,5? Component form 3,5. I want to the nearest hundredth. I want a single angle of rotation. Of course, that would be from east as 0. What is the bearing of a negative 2, 2? Bearing implying a compass rose. Number 3, can you understand what that's the vector u has component form of 7, 2. Find that. And what is the direction of the same vector u? Okay, good luck, and we'll see you next time.